So welcome to Chapter 6, which is mainly about pipe flows. So by way of introduction, let's get started with laminar versus turbulent flow. So laminar flow, again, is the very smooth flow. We could do analytical Navier-Stokes types of solutions. If it's a simple geometry, it could be 2D, it can be steady. Again, it's that nice, smooth flow, and that occurs at low Reynolds numbers. Turbulent flow, on the other hand, is that chaotic, crazy flow. So turning on your faucet, for instance, if you turn it on very slowly at the beginning, you're going to get nice, smooth, you can see through it, the flow, that's laminar flow. Turn it on further and suddenly it becomes white, it becomes noisier, it splashes around, that's your turbulent flow. Turbulent flow is a lot more complicated to try to solve. It's always unsteady, there's eddies in it, it's always 3D because it's chaotic and swirling all around. It tends to entrain air in it if it's in contact with air. It mixes up a lot. Way too complicated for us to solve with Navier-Stokes. So with turbulent flow, we're going to automatically turn to experiments or CFD. And it occurs at high Reynolds numbers. So there's your laminar flow versus turbulent flow. There is an area in between, we call that transition, and that's where the flow is becoming unstable. Can't really decide if it wants to be laminar or turbulent. So it does a little bit of both. It will start out laminar, and then maybe you'll get a ripple or two, and then go back to laminar. So it can't quite make up its mind at that point. But then you go a little bit higher in velocity, and suddenly it's going to be completely turbulent and all chaotic and crazy. Okay, so Reynolds number. Again, these Reynolds numbers determine whether it's laminar or turbulent, and it's also used in all of our experimental stuff. It's used everywhere pretty much. It's a very important parameter. Reynolds number, we saw this before in our Chapter 5 non-dimensional analysis stuff. So our Reynolds number is basically, it's going to be density times velocity times some length scale over viscosity. Okay, so our length scale for pipes is going to be diameter. So anytime we have anything round, normally it's going to be diameter as the length scale. The velocity that we're going to use for pipes is going to be average velocity. This can also be written, since mu over rho is nu, our kinematic viscosity, you can just remember it as Vd over nu. Remember venereal disease over nu? Makes it easy to remember. Our V again is V equals our average V, average velocity, because remember velocity is going to be changing as you go across the pipe. It's zero at the walls because of the no slip condition, and maximum in the middle. D is the diameter of the pipe, and nu equals mu over rho, and that's your kinematic viscosity. Okay, so the critical Reynolds number, meaning the Reynolds number where it transitions from laminar to turbulent for pipe flow, is 2300. Okay. So below 2300, approximately, and this is, depends on a lot of things, but approximately at 2300, it'll transition from laminar to turbulent flow inside of a pipe. This 2300 is something that you're going to remember because we're going to use it a lot. But remember, it only applies to pipe flow. So when we get to flow over a flat plate, for instance, in external flow, that will have a completely different critical Reynolds number. So try to remember that this is only for pipe flow. Okay, so below the critical Reynolds number, flow will be laminar. Remember, low Reynolds number is laminar, and high Reynolds number then is turbulent. Okay, another little definition here, internal versus external flow. Internal flow isn't just inside something, it's surrounded by walls of some sort. So a pipe, for instance, is internal flow, and that's what we're doing now. Next chapter, Chapter 7, will be external flow. For example, flow over an airfoil, that would be external flow. a wing. Okay, so this chapter, internal flow, so let's get into internal flows. Let's look at pipe, okay? And this is at an entrance to a pipe, so these curvy lines indicate where flow is coming in. So let's say out here we have just a uniform velocity. So if I draw a velocity profile, it just looks like that. It's all at a constant velocity, U naught, call it. Okay, so let's say the beginning of the pipe is here at x equals 0, and x is going this way along the pipe. What is going to happen is when this velocity profile first hits that pipe, well, the pipe hasn't had a chance to affect the velocity at all. But the velocity right here at the edge has to be 0. Okay, so if you go into this pipe just a little bit, there's going to be a very short area where the velocity is going to go from 0 out to almost this, or actually a little higher than what it is here. And then it's going to do the same thing. This is round, remember. These are not two plates. This is round. So you're going to get a velocity profile that looks something like that. It's flat in the middle, and just the edges are going to decrease down to 0 velocity. You go in a little bit further, and the walls then have had a little bit more of a chance to affect the flow further towards the center. So you're still going to have a flat area in the middle, but it's going to be smaller. It's straight. So it'll look like that. So it's kind of a blunt parabola here. It's flat in the middle. Okay, eventually you're going to get to the point where the walls are affecting the flow all the way across. And at that point, you will get your parabola. Okay, the area here, if we're looking down at the entrance part here, there's only a little bit of space here where the velocity is changing. Then the velocity is flat. Do you remember where the velocity is changing? There was a term for that. That area, that region, it's called the boundary layer, remember? So all around, right near the pipe surface, you're going to have the boundary layer. Okay, and that boundary layer is going to get bigger as you go along. So if we draw the boundary layer, it's going to go to where it becomes flat, right? Eventually that boundary layer meets in the middle. Okay, and now the walls are affecting it all the way across. The velocity is changing all the way across. Shear stress is important then. All the way, it's going to be non-zero all the way except for right here at the point, and then it's going to be non-zero again. Once we get to this point, we're going to say that after this, the velocity is not changing, and if you remember, we had a term for that. If the velocity is not changing in the flow direction, that is called fully developed. So now we're at the fully developed region. And that means u is a function of r only at this point, not x. And the boundary layer has met in the middle. Okay. The area out here from the beginning of the pipe up to where it becomes fully developed, that is called the entrance length, or LE for short. All right, and you're going to see this again in heat transfer, not only like this with the velocities, but also with temperatures, because the same kind of thing happens with temperatures if you have a hot pipe and a cold fluid, for instance. Okay, some notes. Again, because of the no slip, that's why you have 0 here near the walls, but the walls can't affect the flow all the way out to the middle right away. It takes a little while. Okay. Because of conservation of mass, if the walls are holding the flow back, in order to get that same total flow at this point, and this point, and this point, and conservation mass says you have to, then the velocity has to be higher in the middle than it is on average than the average, let's say. It's equal to the average here at the entrance. Higher in the middle as you go towards the fully developed region. Okay, so again, the boundary layers meet in the middle where it becomes fully developed. And this is the definition of the entrance length again. For x is greater than the entrance length, the velocity is now not a function of x anymore. And that's, the Navier-Stokes kind of equations they were solving with were all fully developed because otherwise it just gets too complicated. So we call it fully viscous for NER beyond the entrance length. And this isn't quite true. This is not the lie of the day, but it's only 0 at the center. Shear stress is only 0 at the center beyond the entrance length. Okay. So stop here and do quiz questions 1 through 3.